So the question was that why do we need tensors? Okay, so a tensor is an entity which is independent of the system of coordinates to which its components are referred. And in the mathematical formulation of physical laws, only those quantities which possess such invariant properties can occur, and these are scalars, vectors, and in general, tensors. So any other quantity that are not possessing these invariance properties just cannot occur in the mathematical representation of the physical law. So if you consider scientists sitting at different places and measuring the quantities with their own instrument, then each one of them has chosen a frame of reference that is independent of others. So the measurement made by the different scientists should not differ. Within the limits of the experimental error, it can be, slightly there can be some variations, but the physical quantities should have the same value, should not differ too much. So this is actually much more closer to the principle of invariance. So physical phenomena appear to be the same for all the observers who are stationary relative to each other, independent of the position of each observer and the orientation of the frame of reference of the each observer. Okay, so I hope this part is clear. Now, there are some simple rules for checking the correctness of indices in a tensor equation. So first rule, what is the rule for checking the correctness of indices? A free index should match in all the terms throughout the equation. Okay, the first rule is that a free index should match in all terms throughout the equation. So this means that if a free index occurs as a contravariant index in one term, it should occur as a contravariant index in each term of the equation. Okay, I'll give one example. For example, A beta alpha plus B alpha beta. Okay, this is wrong. This is not possible. Why? Because here this beta is contravariant index, right? Beta is contravariant. But in the next term, beta is becoming covariant. So if a free index is appearing as contravariant in one term, then it should always be used as a contravariant. You cannot change in the next term because this is one single equation, right? If I write this is equal to some C, then this is an equation. So in an equation, always contravariant, a free index, if it is contravariant in one term, it has to be contravariant throughout. And if it is covariant in one term, it has to be covariant throughout. You cannot mix and match. Therefore, this is wrong. Okay. That is the first rule. Now, second rule. A dummy index should match in each term of the equation separately, and a dummy index may occur only in some of the terms of an equation, but when it occurs, it should occur twice, and once in a contravariant position and once in a covariant position. Okay, so a dummy index means dummy index is an index which is summed over, so it should appear twice. It should appear twice, not only that it should occur twice, but once in contravariant position and once in covariant position. Okay, for example, A alpha alpha beta. Okay, this is right because here alpha is dummy index because it is summed over and it is appearing twice, also once as contravariant and once as covariant. So this is right. Okay, this is the correct notation because a dummy index, when it occurs, it should occur twice, once in a contravariant position and once in a covariant position. Now the third rule, no index should occur more than twice in any term. Okay, no index should occur more than twice in any term. For example, A, alpha alpha is correct, but A, alpha 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 is wrong. No index should occur more than twice in any term. Now, the fourth and the last rule is that when a coordinate differential, such as partial derivative of xi, occurs in a term, okay? When a coordinate differential, such as partial derivative of xi, occurs in a term, this I has to be regarded as a contravariant index if partial derivative of xi occurs in the numerator, like this. Then I is contravariant. And if it occurs in the denominator, it has to be regarded as covariant. For example, if it occurs like this, here I is covariant. Okay. So whenever a partial differential or a coordinate differential such as partial differential of xi occurs in a term, I has to be regarded as a contravariant index if the partial derivative occurs in the numerator, and as a covariant index if it occurs in the denominator. Now we'll do some problems regarding these rules. First one, if A mu rho is a mixed tensor, it's a mixed tensor of rank 2, then show that A rho is also a tensor. Okay, so given A mu rho is a mixed tensor of rank 2, so that is already given, and we have to show that A rho is also a tensor. So first we'll write the given quantities. So given that A mu rho is a mixed tensor, then I can write the transformation rule for A mu rho. So I'm writing A prime alpha beta is equal to partial derivative of x prime alpha with respect to x mu, partial derivative of x rho with respect to x prime beta. Okay, so this is the transformation for a mixed tensor of rank 2. So this is already given. It is given that A mu rho is a mixed tensor of rank 2. Now I have to show that A rho is a tensor. For that I have to put alpha equal to beta. Okay, alpha equal to beta, so that I have to show that A rho is also a tensor. Now I am going to substitute. A prime alpha is equal to partial derivative of x prime alpha with respect to x mu, then partial derivative of x rho with respect to x prime alpha, because this beta is now equal to alpha, right? So here also I have to put alpha, and A mu rho. All the other things are as it is, only alpha is equal to beta. Okay, I'm just putting alpha equal to beta. Now here we can see this will get cancelled, and I have partial derivative of x rho with respect to x mu, A mu rho. Now this is the Kronecker delta of rho mu A mu rho, right? Now this will be 1 only if rho equal to mu. Otherwise, if rho is not equal to mu, then it will be 0. So I don't have to take this part. I have to take only rho equal to mu, right? Otherwise it will go to 0. Then I have to put, wherever mu is there, I have to put rho. Then I'll get A rho rho, right? So left hand side is equal to right hand side. See, even after transformation, this quantity is remaining the same, which means that it is a tensor. Okay, so we have proved that A rho rho is a tensor. I will do one more problem and then we'll go to the next topic. Now, second problem. If A mu rho sigma and B theta lambda are tensors, then show that A mu rho sigma B mu lambda is not a tensor. Okay, so first it is given that A mu rho sigma and B theta lambda are tensors. So we can write the transformation for A and B. Okay, so I'm going to write A prime alpha beta gamma A mu rho sigma. I have to write the transformation. Partial derivative of x prime alpha with respect to x mu. Partial derivative of x prime beta with respect to x rho. Partial derivative of x sigma with respect to x prime gamma. Now I have to write for b theta lambda. Right? So b prime phi delta and b theta lambda. I have to write partial derivative of x prime phi with respect to x theta, partial derivative of x lambda with respect to x prime delta. Okay, now I have to multiply these two. A prime alpha beta gamma b prime phi delta is equal to partial derivative of x prime alpha with respect to x mu, partial derivative of x prime beta with respect to x rho, partial derivative of x sigma with respect to x prime gamma, partial derivative of x prime phi with respect to x theta, partial derivative of x lambda with respect to x prime delta, then multiplied by A mu rho sigma and B theta lambda. Okay, now we have to go and check what we have to prove. So here I have to substitute, see, mu, and here it is theta, here it is mu, here it is mu. So I have to substitute theta equal to mu, right? So this part should be equal to this part. Otherwise, here I have to substitute beta equal to 5. Sorry, alpha equal to 5. Alpha equal to 5 I have to substitute. So I am going to put alpha equal to 5 in the above expression. Then I will get partial derivative of x prime alpha with respect to x mu, partial derivative of x prime beta with respect to x rho, partial derivative of x sigma with respect to x prime gamma, partial derivative of x prime alpha with respect to theta, then partial derivative of x lambda with respect to delta. All other things as it is. B theta lambda. Now you can see that this term, so I have on the left hand side, I'll write the left hand side also once again here, okay, so that you can compare it. B prime alpha lambda. So here you have to see these two terms in the brackets. So whenever in a partial derivative, whenever the index is appearing in the numerator, then it is contravariant, right? So here you can see that there are two contravariant alpha on the same equation. Okay, so the above equation do not transform like the components of a tensor of rank 3 because of this factor. Okay, because of the presence of this factor, the above equation do not transform like the components of a tensor of rank 3. Okay, therefore if one index of a tensor is equated to a similar index of the other while taking the inner product of the two tensor, the resulting set of function is not a tensor. Okay, so if one index of a tensor is equated to a similar index of the other while taking the inner product of the two tensors, then the resulting set of function is not a tensor. Okay, so I hope this part is clear. Now we will go to the next topic. Next topic is tensor densities or relative tensors. Okay, tensor densities or relative tensors. So the moment you see the word densities, don't think that it is really a density or something like mass by volume. No, it's not like that. Okay. So we have seen that the scalars and vectors are a subclass of tensors. For example, tensor of rank 0 is scalar and tensor of rank 1 is vector. Okay, so scalars and vectors are subclass of tensors. But do you think that tensors are the ultimate one, or is there anything that is much more general and tensors can be considered as a subclass of something? So, can you think of something which is much more general than tensors? Okay, then comes tensor densities. So, tensors can be considered as a subclass of much more general class of quantities called as tensor densities. Okay. So tensors can be considered as a subclass of a more general class of quantities called tensor densities. A tensor density transform like a tensor except for the appearance of an extra factor, okay, which is the Jacobian of the transformation of the coordinates. So I can write, I'll represent tensor densities as script T. Okay, I'll represent something like this. So this is tensor density. So mu is contravariant index, nu, etc. are the covariant index. Then I can write the transformation. I can write the transformation. The script T prime mu nu is equal to, now there is an extra factor. It will transform just like the tensor, but there will be one extra factor which is called as the Jacobian of the transformation, which is raised to a weight w. Okay, otherwise other things are the same. X alpha, partial derivative of x beta with respect to x prime nu. Okay, so a tensor density transform like a tensor except for the appearance of an extra factor. Okay, an extra factor which is the Jacobian of the transformation. Jacobian of the transformation raised to a power which is w, where w denotes the weight of the tensor density, and this w can be a constant. W is a constant and it can be positive or negative integer. Okay, it is weight, can be positive or negative integers. Okay, so in the Jacobian, this dou x prime will come in the numerator and partial derivative of x will come in the denominator. This is the Jacobian, and Jacobian raised to some w. Okay, w is the weight of the tensor density and it can take positive and negative integer values. Now, tensor density of rank 1 is called a vector density. Okay, a tensor density of rank 1 is called a vector density of weight w. For example, t prime mu. Okay, this is a tensor density of rank 1, which is also a vector density of weight w. This can be written as the Jacobian raised to a weight w. Then suppose this is going to alpha, then I can write x prime mu partial derivative of x alpha. Okay, a tensor density of rank 1 is called a vector density of weight w. A tensor density of rank 0 is called as a scalar density of weight w. Similarly, a tensor density of rank 0 is called as a scalar density of weight w. So I can write a tensor density of rank 0. So I don't have to write anything. No rank 0 will transform like this. This is the scalar density of weight w. And now how can you reduce it to the ordinary tensors? So tensors are a subclass of tensor density. Okay, so when does that happen? So you can say that ordinary tensors are tensor density of weight 0. If the weight goes to 0, then the tensor density will become ordinary tensors. Okay, so whenever the weight goes to 0, the tensor density will become ordinary tensors. So tensors are subclass of much more general class of quantities known as tensor densities, and it is represented by the Jacobian with raised to a weight 0. Okay, now we will consider the example of scalar density. Okay, example for scalar density. Now consider the transformation. So this is tensor. Okay, a tensor T. This is not tensor density, this is tensor. I am representing it by T. T, which is going to T mu nu. So the transformation can be written as x mu x prime alpha, partial derivative of x nu, x prime beta. Okay, so this is a tensor. Now I am going to take determinant on both sides. Okay, so determinant of t prime alpha beta is equal to determinant of now partial derivative of x mu, x prime alpha, x nu, x prime beta. Let this be one quantity and t mu nu. Okay, so let this be A and let this be B. Then determinant of A, B will be, we know the formula, determinant of A, B is determinant of A multiplied by determinant of B. Right? This is just in the matrix notation. So if you have a matrix multiplication A multiplied by B, then the determinant of AB will be determinant of A multiplied by determinant of B. Similarly, this tensor equation is also can be represented by matrices. So if I take the determinant of this quantity and this quantity, then the determinant will be, I can write as determinant of the first term, right, multiplied by determinant of t mu nu. Okay, now this determinant is nothing but partial derivative of x by partial derivative of x prime determinant, and there are two terms, right? So I have to write square. Okay, then determinant of t mu nu, and on the left hand side we had determinant of t prime alpha beta. So I'll write here determinant of t prime alpha beta is something like this. So here you can see some quantity, but I'm comparing it with the Jacobian. So in the Jacobian, x prime should be on the numerator and x partial derivative of x should be in the denominator. But here I am seeing something inverse. So I'm just trying to make it in the other form. Okay. If I want to make it in the other form, then I have to write partial derivative of x prime with respect to x, but this 2 I have to change it to minus 2. Okay, then determinant of t mu nu. So you can see that determinant of a tensor will transform like a tensor density, or here scalar density. Okay, determinant of a tensor will transform like a tensor density of rank 0, which is scalar density. Okay, therefore if t alpha beta is a tensor, then determinant of t alpha beta is a tensor density, or simply you can say here in this case it is scalar density, because tensor density of rank 0, tensor density of rank 0 is scalar density. Okay, so now we can apply this to the fundamental covariant metric tensor also. So here t alpha beta is a rank 2 tensor, right? This t alpha beta or t mu nu is a rank 2 covariant tensor. So we know another covariant rank 2 tensor, which is our fundamental metric tensor. So I'll take that. Why don't we take it directly? So G prime alpha beta, this is the fundamental covariant metric tensor. So let's consider the fundamental covariant metric tensor G prime alpha beta. Okay, so let the transformation be partial derivative of x mu with respect to x prime alpha, partial derivative of x nu with respect to x prime beta. Okay, Now I have to take the determinant. If I take the determinant, it will be G prime. Here G denotes the determinant of G prime alpha beta. Okay. And here it will be partial derivative of X. Then determinant of G mu nu will be G. Determinant of G alpha beta prime is G prime. Okay. This is the determinant. This is the determinant. Okay. So G prime is equal to partial derivative of X with respect to X prime whole square. Now it follows that the determinant of a covariant fundamental metric tensor G mu nu transforms as a scalar density of weight minus 2. Okay, because here it is in the inverse form. So I can write G prime is equal to partial derivative of X prime with respect to X whole raised to minus 2 times G, right? So a covariant fundamental metric tensor G mu nu transforms as a scalar density of weight minus 2. Now similarly, it can also be shown that the determinant of fundamental contravariant metric tensor G mu nu transforms as a scalar density of weight plus 2. Okay, so you can similarly show that in the case of a fundamental contravariant metric tensor, the G mu nu transforms as a scalar density of weight plus 2. So these are all scalar density. But there is also a tensor density that is quite useful in curved manifold. So the next topic is the Levi-Cevita tensor density. So we are all familiar with the Levi-Cevita tensor symbol, right? Epsilon, alpha, beta, gamma, delta. It can take three values. Plus 1 if alpha, beta, gamma, delta are even permutations. Minus 1 if alpha, beta, gamma, delta are odd permutations. And it will take the value 0 if any two indices are the same. If any two indices are same, then it will take the value 0. Now, the catch is that if epsilon, alpha, beta, gamma, delta is a tensor, then it has to be invariant. That is, under a change of coordinate system, it has to change. It should change as epsilon prime, alpha, beta, gamma, delta is partial derivative of, suppose it is going to epsilon, mu, nu, lambda, rho. Then it should transform like partial derivative of x prime alpha with respect to x mu, partial derivative of x prime beta, x nu, partial derivative of x prime gamma with respect to x lambda and partial derivative of x prime delta with respect to x rho. Okay, but by definition, the components of the Levi-Cevita tensor must be the same in all the coordinate system. It has to be either +1, -1 or 0. Okay, the components should not transform like this. It should not transform. For that, the contribution from the coordinates must get cancelled. So these are the contribution from the coordinates. Contribution from the coordinates should get cancelled. So epsilon should not transform under a change of coordinate system. For that, I have to cancel all the contribution from the coordinates. So for this, I have to introduce another factor in the same equation. So here I can see that the contribution has a form partial derivative of x prime by partial derivative of x. So it is in this form. So I have to multiply it by the inverse. For example, I have to introduce a factor. Partial derivative of x with respect to x prime, something like this. I have to multiply so that these two will get cancelled. Epsilon prime alpha beta gamma delta can be written as partial derivative of x prime, then partial derivative of x prime alpha with respect to x prime mu. So if it is going to epsilon mu nu lambda rho, then partial derivative of x prime beta with respect to x nu, partial derivative of x prime gamma with respect to x, partial derivative of x prime delta with respect to rho. Okay, here you can see that the partial derivative of x with respect to x prime, and this will give a contribution partial derivative of x prime with respect to x and epsilon mu nu lambda rho. Now these two will get cancelled. Okay, and you will get epsilon prime is equal to epsilon. Okay, epsilon prime is equal to epsilon. So then it will be a tensor. Otherwise, it will not be a tensor. So for that, I have introduced this term, this first term. Okay, and these are the remaining terms. So partial derivative of, I can write x prime with respect to x and then -1, right? This can be written like this. Then the remaining terms. Okay. So in other words, I can say that the contravariant Levi-Cevita tensor density. This is contravariant Levi-Cevita tensor density must transform as a tensor density of weight -1. Okay, so in other words, I can say that the contravariant Levi-Cevita tensor density. Now we know that Levi-Cevita is not a tensor, it is a tensor density. Why? Because it has to be a constant in all the coordinate system. The components should not vary. So if epsilon alpha beta gamma delta is a tensor, then that is not possible. It will change. So it is not a tensor, it is a tensor density. And the contravariant Levi-Cevita tensor density must transform as a tensor density of weight -1. So similarly, I can say the covariant Levi-Cevita tensor density must transform as a tensor density of weight +1. Okay. So similarly, I can also say that the covariant Levi-Cevita tensor density must transform as a tensor density of weight plus 1. Contravariant will have a weight minus 1 and covariant will have a weight plus 1. Okay. So in a flat space-time, we know that the volume element must remain invariant. Okay. In Lorentz transformation, you might have learned in the Minkowski space-time, that is the Minkowski space-time is the flat space-time. In the flat space-time, the volume element should remain invariant under Lorentz transformation. So under the Lorentz transformation, the volume element remains invariant. Okay, so I can write the volume element as d4x. Okay, if I am writing the transformation, then d4 prime x must be, you can write as partial derivative of x prime mu with respect to x nu. Okay, this is a transformation for the Lorentz transformation, and we know that this is lambda mu nu d4x, and in Minkowski space this Jacobian is 1, that we have already learned in special theory of relativity, right? So this is equal to d4x. So this is only in a flat space time. Now in a curved manifold under a general coordinate transformation, so in a curved space time, now we are going to look at the curved space time. In a curved space time, x prime mu is transformed to x nu. Okay, therefore the volume element will transform like this. Now this Jacobian is no longer unity. Okay, so the volume element in a curved manifold behaves like a scalar except for this determinant factor. So except this factor, it will behave as a invariant. Now we have seen that the covariant G mu nu. Okay, so G prime is equal to partial derivative square G, right? This we have just now proved here. Yes. Okay. Now rearranging, I can write partial derivative of x prime by partial derivative of x determinant can be written as root of g by g prime. I'm just rewriting, okay, rearranging, and I can obtain something like this. Now I can introduce a minus sign here and a minus sign here so that there is no change. Okay, I can just introduce a minus on the numerator as well as the denominator. Okay, then I will get d4 x prime is equal to partial derivative of x. This we have already defined here. Okay, so here I have to substitute d4x. So instead of partial derivative of x prime with respect to x, I have to substitute this. So here I am going to substitute under root minus g by minus g prime d4x. Now I'll multiply here. G prime d4 x prime is equal to root of minus g d4x. So in a curved space-time, the volume element by itself is not invariant. Only if you multiply the volume element with root of minus g prime on the left-hand side, that is in the new coordinate system, and root of minus g in the old coordinate system, this is invariant. This quantity is invariant. Okay, but d4x prime is not equal to d4x. The volume element as such is not invariant, but if you multiply with this quantity, then it is invariant. Okay. Yeah, so hence you can also extend this to the tensor densities. So the tensor density script t mu nu can be written as partial derivative of x prime with respect to x raised to a weight w. Okay, suppose if it is going to alpha beta, then partial derivative of x prime mu with respect to x alpha, then partial derivative of x beta with respect to x prime nu. Okay, so here instead of partial derivative of x prime with respect to x, I can write as root of minus g by minus g prime. Now the whole thing raised to w, and the other quantities will remain as such. Now I can again cross multiply. So root of minus g prime script t prime is equal to root of minus g. Now this is raised to w also there, okay? Is to w and all other terms. Then script t alpha beta. Okay. So this quantity has the same rule of transformation as any ordinary tensor. So if you see, this entire quantity can be written as, see here there will be this transformation rule, right? Partial derivative of x prime mu with respect to x alpha, partial derivative of x beta with respect to x prime nu. Then I can write root of minus g raised to w alpha beta. So this quantity is transforming like a tensor. If I combine this root of minus g with the tensor density, and on the right hand side also root of minus g raised to w, if I combine it with the tensor density, then you can see that it is transforming like a tensor, which means that a tensor density of weight w, a tensor density of weight w, when multiplied by a factor minus g raised to w, is a ordinary tensor. Okay. Now this is an, or when I multiply a tensor density with a factor with this factor, then it will become an ordinary tensor. Okay. Similarly, by the same way, if you multiply an ordinary tensor by minus g raised to w, then it will become a tensor density of weight w, like this. Okay, this is primed quantity, this is unprimed quantity. So whenever you multiply a tensor density of weight w with this particular factor g prime raised to w for tensor prime, tensor density prime, and g raised to w for tensor, then the tensor density will become a tensor. It will transform like a tensor. For today, we'll stop here.